Okay, let's solve the theory of exercise 8. So I am assuming we're going to just use the theorem very loosely, like this, just like that. Okay, so h of 1 is, so we have a sequence of integers, right? Sorry, sequence of real numbers? Real numbers. Yeah. And essentially that means we have a map from the set of integers to the real numbers. And there's a bijective correspondence, that's whatever. But yeah, so h of 1 is equal to g of 1. And if we define h of I to be h of I minus 1, which rho can certainly give us, and plus g of I, which rho can also give us because it's a unique value for each. So if we take the function to be restricted to I minus 1, we can certainly get a function that sends this to a real number that's this form, that's of this form, because sums are unique if I'm really getting into it. But yeah, because it's unique by principle of recursive definition, there exists a function such that, yeah, it satisfies. So yeah. And for question 2, we do a similar thing, but we define h of 1 to be g of 1, and h of I is equal to h of I minus 1, which is available to us, plus g of I, which is also available to us. For question 3, the special cases are we just replace the sequence as all A's or as 1, 2, 3, and so on. But yeah, it's the same thing. Okay. For the Fibonacci numbers, yeah. So given that we just want the unique number, let's see. So h of 1 is equal to 1, that's fine. H of 2, we're going to have a bit of a problem because, well, how do we get the 1, right? So, I mean, yeah, we can, okay. So H happens to be a singleton thing, then it's going to give 1. So yeah, the function is defined this way, that if it sends a section of integers from, say, okay, if it's a function from the set 1 containing 1, then give the value 1, right? So that can be the definition. Okay, that's, yeah, okay. Now H of uh, I is equal to H of I minus 1 plus H of I minus 2. And this is fine because it's a unique number. And it's based on the function restricted to I minus 1. So yeah, essentially, so if we're getting a function from, yeah, we're getting a function from section S of I plus 1, no, S of I. And from this function, we're getting two values. So yeah, rho is capable of summing the last two essentially because it's unique. So yeah, the generalized version of a row would be the axiom of replacement, which is not covered here. But yeah, the whole point is that we want something that's unique valued for the set of functions, right? Okay. Now, question 5. Show that there's a function satisfying the formula that. Okay. So how do we show uniqueness? Well, uniqueness. So okay. So h of 1 is 3. That's fine. Now we have to show that h of I is greater than 0 for all I. If we show that, then the square root is unique and well defined and will be done. So how do we show that? Let's see. Yeah. So we can show that by induction. H of 1 is 3, which is greater than 0, fine. And h of I, let's assume that to be positive. Now, h of I plus 1 is equal to a positive square root of positive number h of I plus a positive number 1. And h of I plus 1 is positive because 1 is positive, right? I just mixed it up, but it's fine. And therefore, this is defined to be the positive square root, so it's a positive number. So by inductive, so the inductive hypothesis is true. The inductive step is true, and by induction, it's a positive number. And because it's a positive number and this is a positive number, the whole function is well defined essentially and unique because of the uniqueness of the square root. Okay, yeah. So question 6a, let's see. H of 1 is 3. Let's just go on and then we'll see what the problem, right? H of 2 is 3 minus 1, 2. 3 minus 1, 2 square root of 2. Okay. H of 3 is square root of 2 minus 1. Okay, now is this less than 1? Yes, it is. Why? Okay, I'm not proving it. I think I proved it earlier, but if it's less than 1, then x square is also going to be less than 1. Yeah. So because of that, h of 4 is going to be some square root of a negative number, which doesn't exist. So there's no function. Yeah. And this does not violate the principle of recursive definition because the function has to actually send it to a value of the real numbers, and it is not, right? So the function that it's attempting to define isn't a function that we want. It's not the type of function we're asking for. So because the hypothesis is violated, the principle is not violated. Okay. Yeah, this one might exist. Yeah, let's see. So you just have to show uniqueness, right? Yeah. Mm, okay, h of 1 is 3, h of 2 is, let's see, yeah, h of 2 will be square root of 2, h of 3 will be square root of 2 minus 1, and h of 4 will be 5, right? Yeah. Okay. So all so far so good. And hmm, how do we show that there's a unique function satisfying this formula? Let's see. Okay, so if by totality there are only two cases for hi minus 1, right? So we'll prove it by induction. If we can prove that for each section of integers from h, we can get a unique value, will be good, right? So by totality, there are only two cases to consider, or three cases, but we don't really consider the hi equal to 1 because it's covered, right? So by totality, h of I minus 1 and h of I minus 1, so yeah, they'll either be greater than 1 or less than equal to 1. And we're assuming it's defined till I minus 1, and we have to show that it can be defined as n 1, right? So by induction, we can prove it. H of 4 is defined, so there's no problem in the beginning. Yeah. So in this case, we have a unique value 5, and in this case, we have a unique value that's positive because it's bigger than, right? I think we could have potentially, no, we couldn't have. It's greater than 1, so h of I minus 1 minus 1 is greater than 0. And that means because it's greater than 0, there exists a unique square root. So that's it. Yeah. I have already proven theorem 8.4, and question 8 seems identical. So A is a set. Hmm. Okay, yeah. So we don't have the A naught in this case. That's something new. And for A naught, what we'll just take is S of 1, right? Yeah. So S of 1 is actually what? What is it? It's going to be the empty set, correct? But the empty set is also a function. It's the empty function, right? If you define a function on the empty set, you'll get an empty set. So rho can actually be defined on S1 as a thing, H restricted to S1. That's the empty set. So we can get a value in A, and we'll call that A naught, right? So the A naught is not a problem. Okay. Now, so essentially, I'm proving 8 implies 8.4. Question 8 implies theorem 8.4. Now, what else? Sn is identical to section till n minus 1, so that's not a problem either. And yeah, given that I have just satisfied the hypothesis of theorem 8.4, the principle holds. So yeah.